parallel, and perpendicular parallel, and perpendicular lines. Perpendicular lines intersect just like a T. They always cross at right angles, 90 degrees. Parallel and perpendicular, parallel and perpendicular, parallel and perpendicular lines.
Hey geometry students, welcome back. Here we are with 3.4 in Big Ideas. We're talking about proofs with perpendicular lines, so we're specifically looking mostly at perpendicular lines here in this lesson. One thing we are going to be doing there is finding the distance from a point to a line, and we'll see that that is always going to be in a perpendicular way. Before we get into that, let's go ahead and take a look at our cartoon for the day. Here's one. It's the sheep health classes. Sheep health classes. Sheep on the screen getting sheared. And this sheep in here is passed out in the back. This guy's like looking down at him. What's going on with you guy, man? Weak. All right, well, let's get into our vocabulary for this lesson. Here it's the distance from a point to a plane there on page 83. So go to page 83, and we're going to write down what the distance from a point to a plane is. And it may be helpful for you to draw this diagram, and I would do that. I would draw a quick little line K, and right there, a little segment. Just put a point there, and then a point up here. Draw a straight line down showing a right angle, because the distance from a point to a line is always going to be at a perpendicular fashion. It says right here, and you want to write the words down as well. So you want to do this. The distance from a point to a plane is the length of the perpendicular segment from the point to the line, and that's what this is right here. So here's your point A, here's your line K. The distance from A to K is always going to be at a right angle right here. So it's not just any line, because we could draw a line from here over to here somehow. We can draw something like that if we wanted to think about, well, we can draw a line from here to here. But that's not a distance right there, because this is not a right angle here from A to K. It's always got to be at a right angle for it actually to be called the distance from a point to a line. So the distance is always got to be at this 90 degrees right angle there. So let's go on to our next part here. So here's an example like the ones we're going to do in just a moment on our extra practice. It says find the distance from point A to BD. So you have line BD down here, point A up here, and you have 3 lines going to it. So you want to find the distance using the distance formula. You want to go not from A to D or A to B. Those are not right angles. You want to go to the one that's at the right angle mark here. That's A to C. So you want to find the distance from A to C. That's what you're doing here. That's what they're saying. Use AC. And so using the distance formula, we figure that out as 5.7. Square root of 32 approximates to 5.7. So that's what we're going to be doing on our extra practice. So let's go over to there on page 84. All right, so here on page 84, 1 through 4, we're going to find the distance from point A to line BC, so just like that example was showing us. And just remind you what the distance formula is. So it's 1 big square root. We're going to subtract x's and square it, plus subtract the y's and square it. So we need 2 points. So that would give us 2x coordinates and 2y coordinates to plug into our formula. So for number 1, we're wanting to find the distance from A here down to this line. So we're not going to do A to C or A to B. We're going to do A to D. So here's what we want to do from A. We want to do from point A to point D. That's the distance. So we want to use these points right here. So -3, 0. And we want to use this one here, -1, -2. So let's go ahead and plug that in to our distance formula here. So our x's on this one would be a -3 and a -1. So -3 minus -1, that's going to change to a double negative. And then we're going to see 0 minus -2 here. And that can also change to a double negative, 0 plus 2. So it'll look kind of like this here. So you have your -3, the two negatives change to a plus. In that first parenthesis, again, 0 minus -2, the two negatives are changed to a plus. And so now we just keep on going. We're trying to find AD. And so we simplify inside here, take 1 away. It's going to be -2 here and +2 in that one. So -2 squared and +2 squared. So -2 squared here is going to give us 4. This is also going to give us 4. We're going to see 4 plus 4. So as we do that, 4 plus 4 in there is 8. So we're getting the square root of 8. And then the square root of 8 is going to give us a decimal. So we want to use a calculator for that. Just hit the square root button. And we can show it here on this little quick easy one. It just says 8 square root. And there it is, 2.82. And it doesn't say to round to any particular decimal point. So, just do it to maybe 2 decimal places. That's typically how far I typically go. Or on this one, I just did 1. So there you go, 1 decimal place. Actually, I did 1 because that last example showed us only 1, 5.7. It rounded it to just 1 decimal place. So might as well just do it the way the example showed us. So that was number 1. Number 2, we're looking at on this one, point A. So we're definitely using point A here. So we're definitely going to use this ordered pair down here. I'll do it right here. So we're definitely going to use the -3, -4 point, but then which of these points, the B, the C, or the D, do we use? We're going to use the one that's perpendicular. So we're going to use point D right there. So for our X's, and I want you to try this one here. I want you to pause the video, use those 2 points with the distance formula, see if you can come up with the right decimal. Just go to 1 decimal place like this, and then play the video and see if you're correct. So go ahead and pause the video and complete number 2. Okay, hopefully you did number 2 and completed that one. Let's take a look at your work. So with the x's, it's going to be like a -3, -3, maybe in the first one. You can have that. And then you have -4, -2 in the second one. So that would work for the y's. So these become -6. This also becomes -6. So we're getting 2 -6 squareds. So -6 squared on each one. That's going to turn to +36 on each one. So we're going to see +36 plus 36 is 72. So we're getting a square root of 72. And on the calculator, that gives us 8.5. So approximately 8.5 units. Remember to round your decimals. So just make sure you round, look at the second one. If we're wanting to round to just 1 decimal place, always look at your second number here and see if it's more than 5, this will go up. If it's less than 5, you keep it the way it is. All right, for number 3, I'm just going to let you get started on this one. So go ahead and pause the video and then do number 3. Find the distance from A to that line. And then play the video and check your work. All right, so you should have checked you're checking your work now for finishing this one. So we're definitely using A. So you can see we're definitely going to use that one. So we'll use A, of course. But which other one are we going to use? We're going to use the one that's got the right angle mark. That's C right here. So the distance is going to be from A to C. So that's the one we want to find. And so we're going to have a -3 -1, probably in that first parenthesis right there, and then -3 minus -1, so that'll be a double negative. So 2 negatives make the positive there for that 1. And so this is going to make a -4 squared, this will make -2 squared when we start to simplify. So this will give us a 16, and this will give us a 4. 16 plus 4 we're going to see in there is 20. And so the square root of 20 on our calculator to 1 decimal place is 4.5 units. And so that's what we got. All right, go on to number 4. Work out number 4 and then play the video to check your work. Okay, so in this one, for number 4, you're checking your work now. Hopefully you got this one answered already. We're definitely using A again. So A is up here. So we got A right up here. And we're also going to use the one, the line that's perpendicular. That's the C again right here, so A and C. So for our distance formula, for the x's, you could say 1 minus 3, and for the y's, 3 minus 2. That would work. And the order really doesn't matter here because you're going to square it. That's why the order doesn't matter. So if I did 1 minus 3, I'm going to get negative 2 squared. If I do 3 minus 1, I'm going to get positive 2 squared. We're still going to get the same thing when we square it. So we come down, we got negative 2 squared and a 1 squared, and then that's going to give us 4 plus 1, which is 5. So we have square root of 5, and on the calculator, the square root of 5 as a decimal is 2.2 units. And so that's our distance. So our distance from A to this line is 2.2 units. All right, so here's our joke of the day. So why does a milking stool only have 3 legs? So it's kind of like been a farm day. We had talked about sheep in the cartoon here. Now we're talking about milking a cow. So why does a milking stool only have 3 legs? Because the cow has the udder. I love that one. All right, so back on page 83, we're going to be doing another vocabulary right here with this. I'll make this a little bigger for us. See that? Perpendicular bisector. So we've talked about bisectors in the past. We've talked about angle bisectors. We talked about segment bisectors. Well, now we're talking about a perpendicular bisector. So that would be a bisector that's going to cut a segment. So you can see on this one we have a segment here. So really it's always going to be with segments. So this is a segment bisector. You can see that right here because the congruent marks. But it's a little more specific. It's actually a perpendicular bisector because it connects, this bisector connects with this segment at a right angle, at a 90-degree angle. So it's right here you want to draw the picture. So make sure you draw this picture next to your words there, your vocabulary in that page 83. And also let's go ahead and write this down. The perpendicular bisector of Q is the line with the following 2 properties. So you want to say, okay, these 2 properties here, N is perpendicular to PQ, right there, that's what you say, and then N passes through the midpoint, M, at PQ. So it's going to go through the midpoint. That makes it a bisector, and it's also going to be perpendicular. That makes it perpendicular bisector. All right, still there on page 83, we have some theorems for this. So we have some theorems with these perpendiculars. So linear pair perpendicular theorem. We know what a linear pair is by now. We should know that. Linear pair always creates supplementary. So there are 2 angles that are adjacent to each other. They share a side and they add up to 180. So they basically are on a straight line. That's what a linear pair is. Linear for a line right there. And basically this is saying if 2 lines intersect to form a linear pair of congruent angles, then the lines are perpendicular. So if your 1 and 2 are congruent, they're exactly the same. That means they're both 90 degrees. That means that this line right here, this G line, is got to be perpendicular then to H. So it's saying here if angle 1 is congruent to angle 2, then we can conclude that G has got to be perpendicular to H. Perpendicular transversal theorem. So we know about the transversal. That's where 2 lines are cut by a transversal. So J would be our transversal here. H and K are your parallel lines. So in a plane, if a transversal is perpendicular to one of 2 parallel lines, what this is showing here, J is showing that it's perpendicular to H, then it's also perpendicular to the other line. So we can conclude that J is also perpendicular to K as well. So if the lines are parallel and J is perpendicular to K, remember this is the perpendicular symbol, then J is also perpendicular to K. And then here's lines perpendicular to a transversal theorem. So this would be kind of the reverse of this. So here we have the, if in a plane, 2 lines, if 2 lines are perpendicular to the same line, then they are parallel to each other. So here we have the P is the transversal. So P is perpendicular to N and it's perpendicular to M. So that's going to show us that M and N can be shown as parallel. So if M is perpendicular to P and N is perpendicular to P, then M and N can be shown as parallel. Okay, so here's just one to look at. It's a kind of a grid here. It shows a neighborhood with different streets, and the lines are highlighted there in red. They are given names, and it's kind of hard to see them. So you have S up here, there's T, and this looks like U. And then this is P, and this is Q over here on the sides. And we're showing some perpendiculars here, these 90 degrees. There's a 90 degree on this one, 90 degree here, 90 degree here. So there's 3 90 degrees in there as well. It just says determine which lines, if any, must be parallel in the diagram. So if we look at it here, if we look at, let's just say, P and Q, these two lines right here, notice S is perpendicular to P and it's perpendicular to Q. So because S is perpendicular to both of those, we can definitely determine that P and Q have to be parallel because of that fact. And also, if you look at S and T right here, where Q goes through them, so where Q goes through S, it's perpendicular, and where Q goes through T, it's also perpendicular. So since Q is perpendicular to both S and T can be shown as parallel. So that's what this is going to say down here. We can conclude that P is parallel to Q and S is parallel to T because of the perpendicular marks in there. And that basically this theorem right here, the lines perpendicular to the transversal theorem. When these two are perpendicular to the same, they're perpendicular to the same line, and they're parallel to each other. All right, let's go on to finish our extra practice. All right, there on page 85, we have just 4 more here. It says determine which lines, if any, must be parallel. Explain your reasoning. So we'll explain it using the theorems we were just looking at. So for number 5, you can see it just has the one mark there. So if there's only one mark, one 90 degree mark here, there's nothing else anywhere else. So that shows us that we can't, there's nothing here, there's no lines. We can't determine, basically the only lines you could determine would be P and Q. Are P and Q parallel? And we can't say that they are because it's not, S is perpendicular to P, but S is not perpendicular to Q. So definitely we can't say that. So for that one, there's no lines that we can determine that are parallel on that diagram. But coming down to number 6 now, you can see there's a couple 90 degree marks. This R is perpendicular to both of these lines, to both P and Q. So because of that fact, we can say that P is parallel to Q, and the reason why is that theorem that we saw before, which is the lines perpendicular to transversal theorem. That's the one that said, R is our transversal here. If 2 lines are perpendicular to this transversal, then those 2 lines are parallel to each other. If you come up here on number 7, we can see, we have three marks here for the 90 degree angles. If we kind of just focus on, we can focus on these 2. It doesn't matter, you can focus on whichever ones you want to first, but you can definitely say, based on, if you think of M going through here as a transversal, M is perpendicular to J right there. M is also perpendicular to K, so that's going to definitely tell us that J and K are parallel. But also if you think of K down here as a transversal, K is perpendicular to N and K is perpendicular to M, so that would definitely show that M and N are parallel. So that's what we can say, M is parallel to N and J is parallel to K, and the reason for that again is lines perpendicular to transversal theorem. I used the little symbol there instead of writing out the entire perpendicular word. And then for problem 8, we see this down here, 1 and 2 are congruent right here in this little part, this little intersection. 1's congruent to 2. So that's that linear pair one. If they're the same, we can conclude is that M, or this letter N here, this N is perpendicular to S. So basically that just shows you that this is also 90 degrees. These show 90 degrees, but this is also now showing that these are 90 degrees as well. So that's our linear pair perpendicular theorem right there that tells us that that's a 90 degree angle. 1 and 2 are both 90 degrees. And so because of that, now we can say, well, if you have N going through here, N is perpendicular to S, N is also perpendicular to T, so S and T have to be parallel. And also, if you think of S going this way, S is perpendicular to N here, and S is also perpendicular to M. So M is parallel to N as well. So S is parallel to T, and M is parallel to N. And for the same reason as we had up here, lines perpendicular to the transversal theorem. That's that same reason. All right, so that's concluding our lesson here for 3.4. You want to be able to go on to the assignment now next, and I will see you back on the lesson 3.5.